All right, so that's the end of part number first part of our presentation. Now, section 2, I'll cover some instrumentation hardware that we use in this platform. So, proximal sensing approach to capture biophysical characteristics of plants. I have 3 types that we will be explaining with more detail. So the first one is the thermal response of the canopy, plant canopy, and we use infrared thermometers for that purpose. We also record light reflectance characteristics of the crop with active light sensors. We also measure something on the architectural characteristics of the plant. We use displacement sensors like this ultrasonic sensor on the bottom of this slide, and we have only one dimension captured, so we can determine plant height very easy. We have developed an algorithm to make that more accurate, and there's we will mention about efforts to bring information on plant architecture from 3 dimensions. So that's still work in progress. We also have used extensively laser sensors like the one at the bottom right side with very good results too. On sensor selection, we have worked over a list of what we call critically important specifications of sensors, things that need to be studied before selecting one particular sensor. And the first one that we deal with all the time is communications protocols. Are those sensors communicating serially or with analog signals? And if it's serial communications, is that RS-232 or RS-485, or the one that we see more often now is SDI 12? So those are important aspects to consider. Field of view is also one very, very important one, because just think about it. You have different sensors mounted on a vehicle, and if they see a different path, a different track at the at the bottom where the plants are located, so that tells you right there that you have to have different vertical adjustment of the sensors. Range of operation. Sensors, there are parts of the in the range, there's parts that are measuring things with accuracy, but sometimes they can get to either too close or too far away, and the accuracy diminishes. So you need to observe what is that proper range of operation. Input power. We obviously prefer sensors that use direct current DC power, and in the range from I don't know, 12 or 24 volts. We can handle those easier. Response time is a very, very important one, because you can think about these platforms moving through the field, and you want to collect data as that platform is moving. So ideally you want a fast sensor. The output format is also an important one, and rugged design, something that you can take to the field and will perform accordingly. So this is a schematic of the system that we have put together, looking at spectral sensors at the front, looking at sonar transducers for plant height at the very back, numbered from 1 to 4, from left to right, IRTs mounted with in different positions. So we have, in this case, 8 IRTs mounted. Let's take a quick look at these sensors from the same picture and describe some of their specs very briefly. So first, let me start with the canopy thermal response with IRT sensors. So we're using these Apogees sensors, infrared radiometers. They have a particular section in the electromagnetic spectrum where they collect they're sensitive to. They're 38 degrees field of view. We have tested vertical or 30 degrees forward inclination. They have analog signals. And the last point that I'm bringing here is the response time of less than 1 second. That's the manufacturer's description of response time. So that tells you right away that you really have to confirm that this is fast enough for your operation or not. Plant canopy spectral response with light reflectance sensors. We're using crop circle, ACS 470, 32 degrees field of view. You can change filters to your applications. We chose to use 670, 720, and 820 nanometers. Now these work on an RS-485 network, and they're relatively fast. We are using these at 5 hertz, and the asterisks mean our own experience, and we have good success with at 5 hertz updates. Displacement sensors, again with these sonar transducers, we used this particular type brand, Pulsar 3dB, 12 degrees beam angle. Now that's not that critical for a sonar transducer, but it still has, it's telling you there's an area where there's maximum accuracy. The output is an analog signal, so it's easy to record. But there's one point here. The signal is updated based on an internal controller, internal chip that we have no control over. So how fast it's going to update information depends on the conditions that it's sensing. So we've seen that we have 2 hertz, twice a second. We can have reliable updates. Faster than that, sometimes, and sometimes we don't. GPS. On the GPS side, again, this is critically important to our work to use GPS to reference the location of the information. What is it? Where in the field is coming? Which row, and which at what point along the rows. So GPS, it's really important for our work. We have used this Outback 320 GPS RTK, real-time kinematics. This is the ultra precise systems. We're using GNSS. The only thing to know about that is that these receivers can track many more satellites from different constellations. So the accuracy is improved by that. This particular unit is the board inside is built by Hemisphere GPS. GPS work with serial output, so you need to deal with those signals in a different way. And John Heun will elaborate on that aspect too. The messages or the strings, the serial communication, it follows a code we call the NEMA code, and we're using different strings. In particular, GGA and RMC gives us position and gives us direction information. Accuracy, we are certain that we have within 1 centimeter horizontal accuracy or better, and on the vertical position we have twice that accuracy. So it's what I'm saying is not as accurate. You lose some amount of accuracy and looking at the vertical position. John also will have a brief time describing why it is so important that we know the vertical position of that antenna as long as the horizontal coordinates of the antenna. Okay, this is my last slide before I pass this on to John, and this carries many messages that I have for the audience. First, to make the point that new machines in production ag are coming with GPS controlled navigation systems. And what's not known, or I frequently hear that people are not aware, is that the GPS signals that are feeding those ultra precise systems, those can be also output to other devices. So the message is the following. If you have access to a machine with RTK, ultra precise level for navigation purposes, very likely you can then obtain those signals with that high level of accuracy without having to invest in a receiver that is very costly. So that's the message. That's the picture here with a Trimble FMX on the left. Take a quick look at the screenshots that we added on the right. And the first thing to look in the top screenshot is that the GPS quality is fixed. And you see that on the right says corrections RTK. So at that point in time, when we took this screenshot, we were receiving a highly accurate position string. At the bottom, you see that this slide says GPS output settings, and it's listing the different strings that we can choose from. So we can choose what strings to output, and we can also choose how fast those updates are happening. So that's a lot of system functionality that you can expand out of existing components in your operation. At this point, I'm going to turn the mic over to John Heun. He will then take on section 3.